Hello and welcome to our only video for step 19 called Indirect Proofs. So step 19 says I can learn to write indirect proofs. This comes from chapter 5, section 4 in our book. So this idea kind of goes back to what we learned back in unit 1 with chapter 2. It's kind of more into the logic side of geometry and solving problems and things like that. So we're only going to talk about this in terms of algebraic proofs, but we can also apply them to geometric proofs. So let's see. When we want to use indirect reasoning, we're assuming that a conclusion was false and then showing that the assumption led to a contradiction. Okay. What we're going to do mostly in this video is proof by contradiction. So basically we're going to say, okay, if this is what we want to prove, we're going to assume the opposite. Okay, so we're going to assume that what we're trying to prove is false. And then it's going to work out that we have some sort of contradiction. And so then the original conclusion was true. Okay, this is also called proof by negation. So we're going to do 3 steps. So the first thing we're going to do is basically assume that our conclusion is false. That's the first thing. So the conclusion is false. Then by doing that, we're actually going to try to prove it with our assumption. And then it's going to lead to a contradiction. And then the original conclusion must be true. Okay, so this will make more sense in just a minute. So, oh, wow. That was weird. Okay, so first we're going to talk about how to basically find the negation or find the assumption that we're going to prove. So, if we start with an if-then statement, so if 6 is a factor of n, then 2 is a factor of n. So what we're going to do is kind of take this conclusion, right? Our hypothesis would be 6 is a factor of n. The conclusion is 2 is a factor of n. And anything that follows then, we're going to find the negation, meaning we're going to find the opposite. So if the original statement wanted 2 as a factor, our assumption would be 2 is not a factor of n. So we're literally just finding the complete opposite. Whatever it says, we're either putting not in there, we're changing symbols. If it's equal to, it's not going to be equal to. So if angle 3 is an obtuse angle, that means, if it is an obtuse angle, we want to make sure that it's not an obtuse angle in our conclusion. So we would say maybe angle 3 is not an obtuse angle. Okay, because if it's not obtuse, it could be right, it could be acute, it could be a straight angle, it could be a whole bunch of things. We just don't want it to be obtuse. I really want to touch on 1a because our next 2 examples are going to deal with this. So if it's x is greater than 5, all we're going to do here is change the sign. So we need to flip it, but since it's just greater than, we need to change it to less than or equal to. Okay, if it was less than or equal to, when we flip it, we would flip it, and then we would get rid of the equal to. Last one, triangle XYZ is an equilateral, so triangle XYZ is not an equilateral triangle. There we go. Bam. Okay, so those are that's just how to write a negation. Those are going to be how we write our assumptions to start. Okay, so for this one, write an indirect proof to show that if negative 3x plus 4 is greater than 16, so that's our given, we want to prove that x has to be less than negative 4. Okay, so we're going to start, we're going to make an assumption. Okay, and our assumption is going to be the contradiction, the negation, like we just tried to prove. Okay, we're always going to change whatever the proof statement is. So we basically want to find the negation of x is less than -4. If we want that to be the complete opposite, we're going to assume that x has to be greater than or equal to -4. Okay, so that's the first thing you're going to do. You're going to assume whatever follows the word then and whatever says whatever the proof is. Okay, so we're going to assume for this equation that x is greater than or equal to -4. So we kind of have two cases here. So our first case is maybe that x actually equals -4. Okay, if x is actually going to equal -4, let's actually plug that in. -3, no, I'm sorry. Yeah, -4. -3 times -4 plus 4 is greater than 16. Okay, -3 times -4 would be +12. +12 plus 4 is 16. So what it wants to say is that 16 should be greater than 16, and we know that's false because they're equal to. So this is a contradiction, okay? 16 is not greater than itself. The other case we have so we've done the equal to. We also need x to be greater than, I keep forgetting the -4. So for this one, we want to look at numbers that are greater than -4 and see if one of them actually works. So if we had our x values up here and then our equation is what's -3x plus 4. I'm going to make like a little chart here. So numbers greater than -4, so more positive would be like -3, -2, -1, and let's just stop at 0. Okay, we just need a few because you're going to find very quickly that we're going to kind of know what we're dealing with. So -3 times -3 would be +9, plus 4 would be 12. -3 times -2 is +6, plus 4 is 10. -3 times -1, +3 would be 7, and then 4. Okay, so the whole idea is that if x is going to be greater than -4, our assumption was that then whatever we plugged into this equation here at the top should be greater than 16. None of these values in our chart, right? 12, 10, 7, 4, none of those values are greater than 16. Okay, so both of these are contradictions. Okay, because whatever values we plugged in did not get us to greater than 16. Okay, so our final statement is our final step is to make a conclusion. Okay, so what we did, let's recap. So we assumed the opposite. We made an assumption and we said, okay, well, if that statement is going to be true, then let's assume the opposite. We plugged in values that satisfied our assumption and it didn't work. Okay, so what we're going to say here is assumption led to a contradiction. So the original statement must be true. And that's all we have to say. There's no other, you don't have to write a big paragraph. You don't have to summarize everything, because in showing that you've proven, okay, if we assumed this and we proved examples of our assumption and it didn't work, then our assumption can't be true original has to be true. All right, so we're gonna skip that one. Maybe we'll come back to it in class. So we're gonna keep going. This one is still algebra based. That's what we're gonna stick with and just learning, how these kind of work and stuff. So indirect proof. So this is pretty important. So I'm gonna highlight this. There's not really a label on it, but okay. So what this says is that in such proofs, it is helpful to remember that you can represent an even number with the expression 2k and an odd number with the expression 2k plus 1. And k is just going to be some sort of integer, meaning like 1, 2, 3, 4, 5, or even negatives as well, or 0. So what this says is if we want to write an even number, the only thing that makes a number even is that it's a multiple of 2. So if we take any number and we multiply it by 2, it's going to make it an even number. Same kind of idea. If we want an odd number, if all the evens are 2k and we want to get to an even number, the odd numbers are just everything in between the even numbers. So if we take an even number and we add 1 to it, we will always get an odd number. Okay, so let's look at our first proof. Write an indirect proof to show that if x plus 2 is an even integer, so that's going to be our given. X plus 2 is an even integer. That's going to go here. X plus 2 is an even integer. Then x is an even integer. Okay, so what I'm going to do is make my assumption. Okay, remember we always are going to change the proof statement what follows then. So our assumption is going to be that x is not an even number or an even integer. If x is not an even integer, then it has to be odd. So x is an odd integer is going to be our assumption. If x is going to be an odd integer, then let's say x is represented by what we know is odd as 2k plus 1. Okay, so from now on, x is equal to 2k plus 1. Then in step 2, we're actually going to basically prove that this is false. Okay, so if we know that x equals 2k plus 1, we're going to plug it in to our given. In our given, it says x plus 2 is even. So if x is 2k plus 1, I'm going to plug it in there for x. So instead of x, I'm going to write 2k plus 1 plus 2. So now the goal here is to manipulate this equation to look like either 2k or 2k plus 1. 2 times a quantity would give us an even number. 2 times a quantity plus 1 would give us an odd number. So if I rearrange this a little bit and I say 2k plus 2 plus 1, I can factor out a 2 from 2k plus 2, and I would get 2 times k plus 1 plus 1. 2 times a quantity plus 1. Okay, if some of you are probably thinking, well, why didn't you combine like terms? If I combine like terms and I said 2k plus 3, the first thing we would want to ask ourselves is, can we factor out a 2? Can this be 2 times some quantity? And it can't, because 3 is not divisible by 2. And if we did 1.5, that's not an integer anymore, and we haven't proven anything. So that's why I did not combine like terms, because 3 is not divisible by 2. If it was, if this was like 2k plus 2, and we factor out a 2, then this would be an even number. But it's not. We have 2 times some sort of quantity plus 1. So this is proving that this should be an odd number. But in our given, we said that it should be even, which obviously is not. It causes a contradiction. So this would be a contradiction because we wanted it to end up as even, and therefore our conclusion would be assumption caused a contradiction. So original statement must be true. And that is everything for step 19.